Hello everyone, I'm Xiuling Wang, a PhD student from Stevens Institute of Technology at New Jersey, US. I'm going to present our work titled Providing Item-Side Individual Fairness for Deep Recommender Systems. This is a joint work with my advisor, Wendy Wang from Stevens. This work is funded by National Science Foundation. Although recommender systems have been demonstrated as efficient and effective, the issue of bias in these recommender systems has raised serious concerns, which can be clarified into two categories: user-side fairness and item-side fairness. Intuitively, user-side fairness requires that users should be treated equally by the recommender system, regardless of their demographic property or their activeness on the recommender system platform. While item-side fairness requires that items should receive equivalent exposure by the recommendations, regardless of their popularity. The item-side fairness can be further divided into group fairness and individual fairness. Group fairness requires that items in popular and unpopular groups should be treated statistically similarly, while individual fairness requires that similar individual items should be treated similarly by the recommender system. In this paper, we focus on individual fairness at item side in recommender systems, due to the relatively few research in this direction. Our contributions can be summarized in the following three aspects. First, we formalized a new notion of individual fairness named alphabet fairness. Next, we designed two bias mitigation methods named embedding-based re-ranking, abbreviated as ER, and greedy substitution, abbreviated as GS, that take different types of input for bias mitigation over recommendations. Third, we demonstrated the performance of both ER and GS on two real-world datasets and a set of state-of-the-art deep recommender systems. Next, I will explain the details of our fairness definition. Alphabet fairness. A recommendation algorithm A provides alphabet individual item fairness if and only if for all items that their distance are less or equal than F, that they must satisfy that their coverage disparity are less or equal than beta, where alphabet are user-specified thresholds. We measure the distance between two items as the cosine similarity between their embeddings. We say the items are alpha similar that if their embedding distance is less or equal than alpha. We measure the item coverage disparity between item I1 and I2 as the distance between their normalized item coverage of these two items in the recommendation list. Next, I will briefly discuss our bias mitigation algorithms. Embedding-based re-ranking takes the user item embedding of the original graph as input. Its objective is to find an optimal ranking policy that maximizes the recommendation accuracy of pi over all users with alphabet fairness constraint. The goal of GS is to substitute the high coverage items in the recommendations with low coverage items while maximizing the recommendation accuracy. We launched an extensive set of experiments to evaluate the performance of both ER and GS. Here are summarized the main observations from our experiments in terms of the bias reduction. We evaluate bias as the percentage of alpha similar pairs of items that violate the beta coverage disparity requirement. We observe the non-negligible bias reduction by our mitigation methods ER and GS ranges in 23% and 93%. Second, in most of the settings, ER is more effective than GS in bias reduction. Then we evaluate the trade-off between the bias reduction and accuracy loss. The trade-off is evaluated as bias reduction over accuracy loss. We observe that both ER and GS algorithms have better trade-offs than the baseline MC. MC is the baseline as cited below. It involves minimum item coverage requirement on all items in the recommendations. And in most of the settings, ER has better trade-offs than MC and GS in most of the settings. Thank you for your attention. Please feel free to contact me if you have any questions. Thank you for your time.